So we're going to talk about atomic theory right now. So when we talk about the atom, you can't actually see the atom. We can't actually take a picture of an atom and all the protons and neutrons, etc., inside of it. So that's what's called atomic theory. Now, a theory is something that's been tested over and 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 never been proven wrong. If it was ever proven wrong, then we wouldn't talk about it anymore, okay? So we'll talk about atomic theory of the atom now. Currently, atoms are the smallest particle in an element that retain the physical properties of that element, okay? So an atom is a complete unit of matter. It's a complete unit of an element. There are only 118 different types of atoms, and those are the 118 elements that exist, okay? So if you just want to write down just a short part of this, these notes will be online, okay? All right. I'm going to go quickly so the video for the people at home will be shorter. Does that make sense to everybody? Okay. The diameter of an atom is really small, 1 times 10 to the negative 10th meters. So that's really small. And atoms are composed of 3 subatomic particles: protons, neutrons, and electrons. And we'll talk about the value of each of those particles, okay? We'll talk about the value of each of those particles. What I mean the value, I mean their charge and their mass, okay? Protons, neutrons, and electrons. So I'm sure that these words are not new words to you, right? Okay. The middle of the atom, the central chocolatey part, is called the nucleus. The nucleus of an atom. That's the middle. All right? Now, if we're going to talk about the atom, we really need to sort of picture the structure. Okay? And I'm going to just pop this up here real quick. All right? Protons. They have a positive charge, and they're in the nucleus. All atoms of the same element have the same number of protons, and protons have a weight of what we consider 1 AMU, 1 atomic mass unit. So protons are positively charged particles in the nucleus. And I'm going to draw you a little picture of this in a second that I'm sure your 8th grade science teacher drew for you. It's going to be the same type of basic picture we're going to start out with. But eventually we will get way, way, way deeper into this than we've ever done. All right. Also in the nucleus, there are neutrons. Okay? Neutrons are in the nucleus. Neutrons have no charge. They're neutral, but they also have a weight of 1. Okay? We'll make a little charge here of particles. Make a little graph here of particles and their mass and their charge. Okay? Now, at this point, I've had several students throughout the years say, Mr. Perkins, something is wrong with this model. Okay? These are students that understand charge. They're like, Mr. Perkins, if opposites attract and like charges repel, how can you only have protons and neutrons in the nucleus of an atom? Shouldn't the protons push apart from each other? Does that make sense to you? Shouldn't protons, if you have 2 positive charges, shouldn't those 2 positive charges repel each other? You understand how magnets work, right? The north end of a magnet is attracted to the south end of another magnet. They stick together. But if you had your little toy cars and you flipped them the wrong way, you can get the little toy cars to push each other apart, right? Well, it should be the same thing with charges. So how will we have these positive charges held close to each other in the nucleus? Okay? And that's a special term that I'll put in your notes, but I won't explain to you too deeply. It will not be on your test. Well, the term will be on your test. It's the strong force. It's something called the strong force, all right? The strong force is what holds the protons in the nucleus together. The strong force is a fairly mysterious force, and it must be incredibly strong because electric repulsion is super, super strong, okay? We're talking about attraction and repulsion of charges. The numbers are astounding. And we know this from Coulomb's law. All right? When you take physics with me, we'll study Coulomb's law. But we're really studying the strong force and particles that are smaller than protons and neutrons at the LHC, which is the Large Hadron Collider, which would be a really fun thing for you to YouTube if you're not familiar with it. So don't write this down. I'm just throwing it out there. Gluons, okay? The strong force results from the exchange of force-carrying particles called bosons. Particles of matter transfer energy by exchanging bosons with each other. The strong force is carried by a type of boson called a gluon, okay? And a gluon is a force carrier. And I can't get too much deeper into this with you other than to say, and they act like a spring. And if you want to read this in your notes, you'll get more out of it than I'll tell you right now. But basically, you know how magnets, the further away they get from each other, the weaker their attraction is for each other. And it's an exponential weakness. And if you looked at the formula for electric repulsion or magnetic, the formulas are the same. And on the bottom, it's the distance squared. So it really reduces magnetic force or electric force the further these things get apart. But with the strong force and those tiny force carriers, they're absolutely the opposite. The further we try to pull them apart, the harder they pull on each other like a spring. Okay? And you can study that online. It's not really part of this class, but I have to mention it because so many people have asked me about it through the years. All right, electrons, this is our last particle. So we talk about protons, neutrons, and the last particle we're going to talk about right here is an electron. Electrons have a negative charge. They're found outside the nucleus. And they basically are super, super light. The mass of an electron is 6/10,000ths the mass of a proton or a neutron. 0.006 of the mass of a proton or neutron. So when we're doing calculations with electrons, we calculate their mass as 0. Of course they have some mass, but we calculate their mass as 0 when we estimate it, because it's only 6/10,000ths of a proton. Or it only has a mass of 6/10,000ths of a neutron. Okay? So we have protons, neutrons, and electrons. And then the modern version of an atom is this. It's called the electron cloud model. And it is unlike anything you've seen before. Okay? Smaller than this in the middle, this is pointing to the area where the nucleus would be. And then these little red marks here are where electrons would appear over time. Okay? Now, I know you've been taught that electrons are going around the nucleus in a circle, or maybe you've even been taught they're moving in some figure eights and other shapes as well, which we'll talk about later. But the fact is, these are areas of high probability where we would expect electrons to appear. Okay? Electrons are constantly coming in and out of existence as far as us being able to perceive them as a particle. Okay? Other times electrons are not observable in the same way because they are simply waves of energy. Don't let that get to your head. I will explain that in detail later, and you will understand it shockingly well. That's a little electron joke. So, this is the current model of the atom. So if I was going to break it down for you, which is my job, I would say, there's a little displacement notes from yesterday. I would say this. The chart you would need to know, the little chart I could definitely imagine you seeing, is this. Mass, right? Charge. Right? And then we have protons, neutrons, and electrons. Okay? What's the mass of a proton? 1. What's the charge of a proton? Positive 1. That's what pro means. Pro means positive. Does that make sense? Okay? The mass of a neutron is 1. But what's the charge of something that's neutral? 0. They're neutral. They have no charge. And we estimate the mass of an electron to just be 0. We just round it off to 0. And then what's the charge of an electron? -1. So which two of these particles, if we look at this little chart we made real quick, which two of these particles would be attracted to each other? Sullivan? That's right. Protons and electrons. Positives and negatives. These two are attracted to each other. Okay? So if we go back to our 8th grade model of the atom, I'm just going to put it up here on the board really quick. I would say in the middle of an atom, you have protons and neutrons. But instead of writing P and N, I'm going to write this little positive sign for a proton, right? And then outside of the atom, we have electrons. Okay? And they can be further and further and further. The electrons are attracted to the protons that are in the nucleus. And that's basically our little model of the atom. Okay? But the real model of the atom today is the electron cloud. They say we have the nucleus, and then we have these electrons that can appear in these areas of high probability. And that's all I'm going to talk about today, because there's a lot of math here, and this is quantum physics, and this is the later chapter. All right? We're going to keep rolling. Element symbols, you already know this. Okay? You know what the element symbols are. Element symbols, basically, is 1 or 2 letters, and the first letter is capitalized. They're not both capitalized. Look at cobalt on your periodic table. If we look at cobalt on your periodic table, isn't cobalt CO? Right? So if cobalt is CO, and you wrote CO and didn't make the second one lowercase, then it would look like you wrote carbon and oxygen. Does that make sense? So first one capitalized, second one lowercase. You feeling it? Okay. We got one last thing to learn today. There are different versions of the same atom, okay? But there are different versions of the same atom, okay? Now the atomic number is the number of protons, okay? That's the most important number. And I'm going to break this down for you on a little card, all right? If you look at the periodic table, it looks like a bunch of cards, okay? And if you're at home, look at your periodic table. It looks like a complicated game of solitaire. Does that make sense to everybody? It looks like a bunch of cards that are laid out. Everybody with me? So if we look at one card of the periodic table, let's look at this one card. Let's look at sodium. Sodium's a really popular element. In the middle of that card, we have the atomic symbol. And then up here is the atomic number. That is the number of protons. It's the most important number. Okay? It's the most important number. And then down here, I'm just going to round it off, you have the atomic mass. The atomic mass is the combination of protons and neutrons. Because remember, the electrons are so small that we don't even count their weight because they don't add up to anything. Does that make sense? You've all seen this, I bet, in the 8th grade, right? Okay, so if we're looking at this, sodium has 11 protons and it has an atomic mass of 23. So if I asked you how many neutrons it had, you would have to do this. You would have to say, okay, Mr. Perkins, I know we have 11 protons, and I know that this number on the bottom, the atomic mass, okay, the atomic mass is the number of protons plus neutrons. So if I wanted to find out the number of neutrons, I could say, okay, the atomic mass minus the number of protons equals 12. There are 12 neutrons. Does that make sense? You have to subtract these two numbers to come up with the number of neutrons. And some of you may say, Mr. Perkins, why don't they just put the number of neutrons on the card? Well, they did. If they tell you this is 23, then you automatically know the number of neutrons is 12. There's no reason to write it up there. Does that make sense? Let's look at another atom. Look at another atom really quickly. All right? Here's the other atom. How about, let's pick out beryllium. Beryllium, number 4, it has 4 protons. That's its atomic number. The atomic number is 4. Beryllium has a mass of 9. Okay? The atomic mass is 9. So that's the atomic mass. So that means 9 is the number of protons plus neutrons. So if we wanted to know how many neutrons were in an atom of beryllium, then we would say 9 minus 4 equals 5. There are 5 neutrons in this particular atom of beryllium. Does that make sense? And that's it. That's us talking about the atomic structure. Now I'm going to film another little lesson about isotopes. Okay, and that'll be just a little bit later.